Welcome back to ECE 501B. In way of announcements, homework number 3 is due a week from Friday, and exam number 1, I'm still taking input on whether or not that will be held on October the 1st. There have been some comments relative to career fair or career services, and so I'm still thinking about that, but if you might just pay attention and keep track of what the timeline is or when we might have that exam. But for now, let's plan on that exam being in 2 weeks on the 1st of October. Today what I want to do is recap with an example the concept of the null space of a map, a linear map, and the range of that linear map. We will then, with that example, actually show that the dimension of the domain is actually equal to the dimension of the null space of T, which is a vector in the domain, plus the dimension of the range of T, and the range of T could be spanning or be in a different dimensional vector space, but the dimension of that range plus the dimension of the null space actually will equal the total dimension of the domain, which is V. We will then look at some injective maps, surjective maps, and how they correlate with dimensions, or what we can say about the dimensions of different subspaces relative to whether the maps are injective or surjective. We will look at or start talking about matrix representations of linear maps, and that's maybe now on a more solid footing or maybe a more comfortable location for where you're thinking of when you're looking at different maps. Then we probably won't get into invertible maps, which are actually both injective and surjective. If you have a linear map that's both injective or one-to-one and surjective onto, then that map is actually invertible. And we will talk about isomorphic vector spaces, or vector spaces that are actually similar in behavior. Going back to our earlier example, this linear map T that maps us basically a dimension expanding map, we go from the domain vector space V, which is of size R3 or living in R3. It's not necessarily of size R3, it's living in R3. And we now have a codomain in R5, which is W. The transformation then takes a point in 3 space, x, y, and z, and maps that into, via a linear map, this combination of 3 points into a location in R5. If we remember back from before, we actually found that a linear combination of -2, 1, 1, or a scalar combination of -2, 1, 1, where x is -2, y is 1, and z is 1, that span is actually in the null space of this linear map, or anything that lies in that direction in R3 will actually map to the 0 vector in R5. That's what we mean by that. Now, how do we determine what the dimension of the null space is? Well, the null space is really, if that's the minimal amount of vectors that span that space, then we can count up the number of vectors that make up that spanning list, and in this case it's actually just one vector, and so the dimension of our null space is equal to 1. Now I could say the null space of T is spanned by a large collection of vectors, but we need to pare those down or remove the linearly dependent vectors. In this case, we only have the one vector, so in fact it is linearly independent, and for that reason now, that's the minimal number of vectors that span the null space, and our dimension of that spanning list is just containing one vector. The dimension of the null space of T is 1, or you could think of that as a line or a one-dimensional line through the origin in this three-dimensional space, in R3. If that's the case, do you remember what we were talking about with a map being injective and its relationship to the null space of that linear map? Here we've just concluded that the null space is non-trivial, meaning we have a non-zero vector that lies in the null space. If that's the case, then is our linear map injective or not injective? Hopefully you remember that if in fact we have a non-trivial null space, then we can use that information to actually allow multiple vectors to map into the same location in the codomain, and for that reason our mapping is no longer one-to-one, and our linear mapping is not injective. And here's an illustration of that. Let's say that we have u1, that's the vector minus 2, 1, 1, and if we go back, that's actually in the null space, and we could plug in minus 2, 1, 1 for x, y, and z in this vector, and I hope that you do that on your own time, but now that actually ends up being the zero vector, since we claim that that is in the null space, or we know that that's in the null space, and it does generate a zero vector. Suppose now we operate, or we map v1, which has 1 in the first coordinate and zeros in the second and third coordinate, or y and z are now 0. That particular vector maps into the location, or the vector in R5, where we look at this particular map and we simply set x equal to 1, y to 0, and z to 0, and we'll see that we have minus 1, 1, 2, and 1 in each of the respective rows, and that's now what we obtain, minus 1, 1, 2, 1, if we map v1 through this linear map T. We can now combine or add v1 and u1 to create a new vector. Let's say that's v sub 2. V sub 2 now takes the first coordinate and adds those up, and we get minus 1. The second and third coordinate each give us 1 apiece. Now if we operate on V sub 2 with T, now we're looking at taking minus 1 wherever x was, 1 wherever y was, and 1 wherever z was. And in the matrix, in the top row, we have plus 1, and minus 3. That was because we had a minus x plus y minus 3z. In the second row, we had again a minus x, but x was already minus 1, so we have a plus 1. Then we had 2y, and we had minus 4z. So that's the second row. The third row is minus 1, plus 1, plus 1. The fourth row is minus 2, plus 3, plus 1. And the last row is minus 1, plus 2. We can now use our expertise in addition and subtraction and find that that now maps to minus 1, minus 1, plus 1, plus 2, and plus 1. And that particular result is identical to what V1 mapped into in R5, minus 1, minus 1, 1, 2, 1. That now shows that T operating on V1 produces minus 1, minus 1, 1, 2, 1. But that's the same thing that happened with when we operated on V2 with T. But if we go back and look, so now we have T of V1 equaling T of V sub 2. But if we look at V1 and V2, those are definitely not the same. V1 had zeros in the last two rows, and V sub 2 does not. It actually has y equal to 1 and z equal to 1. The fact that T of V1 equals T of V2 does not, in this case, imply that V1 was equal to V sub 2, and it needs to. V1 would have to equal V2 if T was indeed injective. In this case, then, T is not an injective linear map. That's an example of where you can create by just adding a vector that's in the null space to any other arbitrary vector and show that the result will give you the same point in the codomain but will not have the vectors in the domain equal to each other. Let's now look at the range of this linear operator T. The range of T is now equal to the span of 1, 0, minus 3, minus 7, minus 2, and another vector 0, 1, 2, 5, 1. And we looked at that last time. We actually set x equal to 1, y and z equal to 0, x to 0, y to 1, z equal to 0, and x and y to 0 and z equal to 1. That produced three vectors. Those three vectors were not linearly independent, and we can then remove one of the vectors from that spanning list of three and end up with just two linearly independent vectors that span the same set or the same subspace that the three did. This is now contained in, or a subset of W, which was R5. But now that that's a minimal spanning list, we can look at the dimension of the range of T. That contains now two vectors, and that's now what the dimension of the range of T equals. This now is because this is the number of linearly independent vectors that span the range of T. We found that there's only two of those, and that then gives us our dimension of the range of T. And look at what we now have. We now can see, I hope, fairly clearly that the range of T, although it lives in a five-dimensional space, does not span all of R5. So R of T does not equal all of W, or R5. So there, that's saying that T is not onto, or is not an onto map, and so it's not surjective. Or the range of T does not span all of W, which W is all of R5. But there is an interesting observation that we can make with what we've learned. We found that the dimension of the range of T was 2. We found that the dimension of the null space of T was 1. And what was the domain's underlying dimension? Well, the domain was actually V, which was R3, and that has a dimension of 3. And if we added the null space of T, of the dimension of the null space of T, with the dimension of the range of T, that too will give us a value of 3. And that's the observation I would like to make. The observation is that the dimension of V, which is the dimension of R3, is 3, and in this example, that was actually equal to the dimension of the range space of T plus the dimension of the null space of T plus the dimension of the range space of T, where this was equal to 1 plus 2. And is that a coincidence? And in fact, that's no coincidence, and that's what we want to show in this next, or state in this theorem, and then we will prove that particular theorem. The theorem, which is theorem 3.4, says the following. Suppose we start with a finite dimensional vector space V, and that's making up our domain. Given V, a finite dimensional vector space, and I might get tired of writing all of that, and so I might just say FDVS for the finite dimensional vector space. Given that vector space and a linear map, which allows us to move away or beyond that vector space into another vector space, suppose now we have the domain's vector space V, which is finite dimensional, and a linear map, and we write that as T belongs to this linear map from V to some other space, vector space W. That's given. Then, with that information in play, the range of the linear map, the range of T, is actually a finite dimensional subspace. And where does that subspace live? Well, that lives in the codomain W, so the range of T is a finite dimensional subspace of W because we started with a finite dimensional domain. And we can also say that the dimension of our domain vector space in fact equals the dimension of the null space of T plus the dimension of the range of T. And we might just point out some facts associated with this relationship. This is actually the dimension of the domain, V. Null space of T is actually a subspace of the domain, which is V, and the range of T is actually a subspace of the codomain, which is W. That's our theorem. Given a domain that's finite dimensional and it's a vector space, together with a linear map, then we can actually make a statement from that information. We can say that the range of that linear map is a finite dimensional subspace of the codomain W, and if we know the dimension of the domain, that's going to equal the dimension of the null space of T plus the dimension of the range of T. And we could then know two of those and calculate the third piece of information from this theorem, or using the results of this theorem. Let's now look at the proof, or a proof of that. First, let's take the dimension of the null space of T to equal some finite value m. If that's the case, we can actually find a basis for that vector space. And what do we know about a basis? We know that it has to have a spanning list, and those the vectors in the spanning list need to be linearly independent. Once we know that the dimension of our null space we're saying is m, then there is a basis. Let's say that that basis is given by vectors u1, u sub 2, and we know that there are m of those since the dimension is m on the null space of T. Now what we haven't said is the relationship between m and the size or the dimension of our domain. So now we're really assuming that m is less than the dimension of the domain. And if that's the case, then we can actually build up or complete the basis for our domain, starting with the basis of the null space of T. And that's due to Theorem 12 in Chapter 2. From that theorem, we know we can, let's say, extend or grow, add to this basis on the null space of T to a basis of V by adding vectors as necessary. So now let's do that, and let's just label those. Now let's let our null space of T vectors, the basis for that, be u1 through un. But now let's augment that with some more vectors we'll label as w, w1, w2, up to w sub m. Let's let that whole set now be a basis, or be the basis, on our domain, or the vector space V. If that's the case, then what can we say about the dimension of our domain? We had m vectors that formed a basis of the null space of T. We needed to add n, or Nevada, more of those to obtain a complete basis for our domain. And we now know then that the dimension of our domain, vector space V, is the sum of Michigan and Nevada, or M and N. Now we really just have a basis for the domain and a basis for our null space. And what we want to do with this theorem is show that the range of T is indeed a finite dimensional subspace, and it has a dimension of, in this case now, little n, or Nevada, in size. Or to complete the proof, we must show that the dimension of the range of t is equal to n, where the range of t is a subspace of our codomain vector space W. So we now need to show that the dimension of the range of T is n, where the range of T is actually a subspace of our codomain W. Let's now just take an arbitrary vector v in our domain. So little v is an element or a vector in capital V. If that's the case and we have a basis for the domain capital V, then we can write or express little v as some linear combination of those basis vectors that are a basis of our domain. We now have a1u1 plus a2u2 up to a sub m u sub m plus, let's say, b1 w1 plus b sub 2 w sub 2 plus dot 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 plus b sub n w sub n. If v belongs to or lives in the domain, then we can linearly combine the basis vectors in that domain to create a representation for that vector v. And that vector v was arbitrary. Now if we have the vector v parameterized in terms of the basis vectors, now what happens when we look at the linear map on little v? Now remember what u1, u2, and u sub m were relative to this linear map T. They formed a basis of the null space of T. They are all in the null space of T, which means that if we operate on those u's with T, they all produce 0, and so we're really, when we look at TV, that particular mapping, we are going to end up with just this B1 times T omega 1 plus B sub 2 T omega 2, where I'm now factoring out the scalars B1, B2, but really we had T operating on B1, W1, but let's now just go ahead and take those scalars out front, which we know we can do by homogeneity, and now we have TV is equal to B1 T W1 plus dot 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 plus B sub M T W sub M. And that was because, or the reason we can write it now and forget all the u's, is because T u sub L was equal to 0. All of those basis vectors u were in the null space of T, and so for all of those L's belonging to the set 1, 2, up to n, those mapped to the 0 vector in W, because the u sub L's are basis vectors in the null space of T. That allows us then to say, therefore, these T, let's say, W sub J's, which is the right-hand side of that, they actually span the range space of T. The reason we can conclude that or make that conclusion is, remember what we started with? We started with V being arbitrary, an arbitrary vector in our domain. Since V was arbitrary, any TV can be expressed as a linear combination of these remaining basis vectors with w's, or the wj's. And that now allows us to conclude or say that thus the list of vectors let's say tw1, tw2 up to tw sub n, that list of vectors spans the range of t. And that's what we wanted to be able to show, that we could actually now find some vectors that span the range of t, and to complete the proof, we now need to show that this spanning list of tw1, tw2 up to twn, that this spanning list is what? We now need to show that that forms a basis for the range of t, and once we have a basis, the basis is linearly independent and spans the range of t. We've already found that those vectors span the range of t. If we can find or show that they're linearly independent, then we simply have to count up how many of those vectors we have, and we know that that actually equals n, and that will allow us to complete the proof. So those vectors in this spanning list need to be linearly independent. If that's what we're setting out to show, that we have a set of linearly independent vectors, let's now consider a linear combination of those vectors in that spanning list. Now consider a linear combination of these tw sub i's, and let's now combine those with scalars that are, let's say, c tw1 plus c2 tw2. Let's now consider the linear combination of all of those such that they sum to 0. And we can show that because we now know that that is a spanning list, and we can linearly combine those vectors to equal 0. Now what we want to show is that the minimal set, and if it is, then that they will be linearly independent. Now once we have this particular relationship between that set of spanning vectors from homogeneity, we can actually push those c's in to scale the vectors w, so that this equation that you now see can actually be written, or the above equation equals t times c1w1 plus c2w2, etc., plus c sub n w sub n, and that's now still equal to 0. But if we now have the linear map T operating on this vector, C1W1 plus C2W2, that vector now, when operated on by the linear map T, when that produces, or that equals 0, what do we know about this vector? Is that vector in any way special? In fact, we know that this particular vector, the sum of W1 through Wn, with this choice of coefficients or scalars, C1, C2 up to C sub n, since that, when operated on by this linear map T, maps to the 0 vector in W, that's now in the null space of this linear map T. If that vector now, this linear combination of W's, which we use to expand the vectors that actually give us a basis for the domain, that particular set or that particular combination, we can say something about that since it's in the null space of T, and we know something about the basis vectors in the null space of T. In other words, so we can expand this vector, which is this vector, which is the linear combination of C1W1 plus C sub n W sub n, we can expand that vector in terms of what vectors? Well, in terms of the basis of our null space, which are these U sub L's. Since that vector, or it, lies in the null space of our linear map T. Well, if we can expand that vector or write it as some linear combination of U's, then we now can say that C1W1 plus C sub 2 W sub 2 up to C sub n W sub n must equal some linear combination of the U's. Let's say that those are now scalars D1 times U1 plus D2 times U2 plus D sub n, M Michigan times U sub n. Now we have to go back to how we built or identified these U's and W's. The U's were a basis of the null space of T, our linear operator. But those were not completely spanning the entire domain. We completed or found a basis for all of our domain by expanding the set of vectors U1 through UM by adding in W1 through W sub n, and that formed a basis. A basis means that they span the vector space, but they're also linearly independent. So we can say, but U1, U sub 2, U sub m, W1, W sub 2, W sub n, since those are linearly independent, those are a basis for the domain or for V, but those vectors are linearly independent by construction. That's how we built those vectors up, or that's how we added in the W1 through W sub n. So by construction, those are linearly independent. If those vectors are linearly independent in this top equation that's still on the page, what do we know about a linear combination of independent vectors? Now if we subtract, let's say, the D's from one side, then we know that that linear combination of vectors is equal to 0, since those are linearly independent, the only way that that can occur is if those C's and D's are indeed all equal to 0. Thus, all of our C sub i's and let's say D sub j's equal 0. Now, if the C's are all equal to 0, we have quite a few buts or injections here, but if the C sub i's or the let's say the C sub i's are equal to 0, then we can draw another conclusion. Then C1 TW1 plus C sub 2 TW sub 2 plus dot 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 plus C sub n TW sub n. We built that initially to be equal to 0. That was right here. We set that equal to, we found a linear combination that made that equal to 0. But now we know that that being equal to 0 actually forced all of the C's to equal 0. What does that tell us? That now tells us that these vectors that span the range of T are actually all linearly independent. Since the only way that that equation is true is if all the C sub i's are 0. This relationship implies that T W sub i's are linearly independent. So the T W sub i's are linearly independent, and they span the range of T. Now we know that we have a basis for the range of T, a set of vectors that span the vector space, or I'm sorry, span this subspace, the range of T, and they are linearly independent. That means that these T W sub i's are in fact a basis of the range of T. Now that that's a basis, what can we say? Well, now we can count up those vectors. Since those vectors are linearly independent, since they're a basis, we can now say that the list of the T W sub i's, we now know that that list is Nevada long. There's Nevada or n vectors making up that list. The list of the TWI's is of length n, and that now allows us to say, so the dimension of the range of T is equal to that n. And that allows us then to reach our conclusion. Therefore, we can now say that the dimension of our domain V, which we built up to be of dimension n plus m, is equal to the dimension of the null space of our linear map T, which was m, plus the dimension of the range of T, which was n. And that now proves theorem 3.4. Now there are some interesting corollaries that come about as a result of that theorem. And those corollaries that follow actually play on this relationship between the dimensions and whether or not we have a non-trivial null space or if we have a non-injective map or if we have a surjective map, which is a meaning that that linear map is onto. So let's look at these particular corollaries. Corollary 3.5 says the following. No linear map from a finite dimensional vector space to a smaller vector space or a smaller one. So now think that your domain is 5 or R5 and your W is, let's say, R4. So we're going from a larger finite dimensional vector space to a smaller one. And that's in terms of dimension. So the linear map, let's say, is mapping between R5 and R4. No linear map that does that can be injective. Another way of thinking of that is we actually have fewer vectors in the output space, or some of our input vectors must produce the same output. Meaning we could have a V1 and a V2, and we say T of V1, that actually might equal T of V2 when V1 and V2 are not equal to each other. And that's non-injective. The picture that you could sort of visualize, now I'm making my blobs representative of their dimension. We now have V here and W here, and a mapping T between those two. Now what we want to do, or what we are saying, is that the dimension of our domain is big, and maybe there's only a unique or a smaller piece of V that is needed to go into this codomain dimension of W. Meaning we can maybe now have a collection of points, so I could draw this several different ways, I guess. Maybe we just say that, maybe it's easier to say, let's now assume that all the points in this particular blue blob actually map to the same point in this smaller space W. That's one way of visualizing that particular result, which says if we go from a big space and map that down into a smaller space dimensionally, then there's no way that that map T can be injective. And the proof of that is actually because in this case we have a non-empty or a non-trivial null space in our domain. And that's the proof. We can now take many different vectors that are different, but yet they map into the same point in the codomain. That's going from big dimension to smaller dimension. That was corollary 3.6. Our next corollary looks at the opposite situation, where we're going from a small domain into a larger codomain. Again, we have no linear map. From a finite dimensional vector space to a bigger one. So now think you go from R3 to R5. In terms of the dimension of those vector spaces, there's no way that we can actually cover or be onto the codomain. So our map, no linear map, can be surjective if it's going from a big domain into, from a small domain into a bigger codomain. The picture we can draw is really sort of just the opposite of what we were doing before. Now we have this mapping T from some small dimensional domain and it's now going into this much larger, or doesn't have to be much larger, but just a larger codomain, and we'll just say that the dimension of W is big. And one way to think of that is to just realize that there are fewer vectors in the input space. And those limited numbers of vectors in the input space are unable to or can't produce all the vectors or directions in the output space, or the range of T is unable to span or does not span W, where W is our codomain. Let's now move on from that. We've been talking about linear maps in general. Let's just introduce this concept of a matrix representation of a linear map. Is there a way that we can actually create a matrix that will contain the information we need to realize a linear map from one vector space into another, from the domain into the codomain? Suppose we are given a linear map, T, that maps between the vector space V and the vector space W, and suppose that we are provided with or given a basis V1, V2 up to V sub n on our domain V, and maybe we have another set of basis vectors, W1, W2 up to W sub M, or Michigan, on W. Our domain then is of dimension little n, or Nevada, and our codomain is of dimension M, or Michigan. We want to now talk about the action of that map on, or between, or using these different basis vectors. The action of this linear map on the, let's say, the kth basis vector v sub k, how can we write that? Well, we're now saying that the linear map applied to this basis vector v sub k, where's that going to take us? Well, v sub k, remember, is a part of, or is a vector in our domain. We now map that through the linear map into the codomain, which means that the result of applying this linear map to one of these basis vectors in our domain V, capital V, must be able to be written in terms of the basis vectors in our codomain, capital W, which means that we can now say that for this basis vector k, maybe we now have 1 comma k w1 plus 2 comma k w sub 2 plus a sub m comma k w sub m. We now can combine those m basis vectors on our codomain in such a way by picking these coefficients, or these scalars, a1k, a2k, such that we can describe the vector that results when we operate on the basis vector v sub k in our domain with this linear map T. And we have how many of those basis vectors in the domain capital V? Well, we have 1 through n of those. So let's now collect all of those into a rectangular grid, or a matrix. These scalars, a's, or these coefficients, for all the, let's say, n vectors v sub k, can be collected in the M by N, Michigan by Nevada matrix as follows. For each of the k vectors, and remember k was our second subscript on the a, so in this first column, let's say that that's a11, a21, so this is now the scalars that scale the basis vectors in our codomain to produce a representation of the linear map applied to v sub 1. This column then, right here, is actually t v sub 1. The next column is a1 comma 2, a2 comma 2, down to a sub m comma 2. This was now the linear combination of our basis vectors in the codomain capital W that are needed to represent the linear map T applied to our second basis vector in the domain vector space capital V. That keeps going. We could say, oh, the kth vector we've talked about. And that just keeps going all the way down to the last vector, which is A1n, A2n, because we had n v's that made up our set of basis vectors on the domain. Let's now see if we can look at an example of that to just get a little bit better feel for this matrix representation, because now what the book might do notationally might not look like a matrix, but let's see if we can now put that into something that looks familiar to us in terms of a matrix. Let's say that we now have a linear map T that maps from R3 to R2. Our linear map T is going to be taking this point in 3 space, x, y, z, and mapping into a point in 2 space, or a vector that has 2 coordinates. And let's say the first coordinate is given by 2x minus y plus 3z, and let's say the second coordinate is 7x plus 5y minus 6z. Let's say that that's now the definition of this linear map. For a given point x, y, z in 3 space, we can find the 2 coordinates in R2 determined by this particular combination, linear combination of the point in 3 space, x, y, z. Now we need a basis for not only the domain, but also the codomain. And let's just pick the standard basis for the domain. V1, let's say, is 1, 0, 0. V sub 2 is 0, 1, 0. And the standard basis, by that I mean the nth coordinate is 1 and all other coordinates are 0. We only need 3 basis vectors in R3, and those are now given by V1 through V sub 3. Just to keep things simple, or maybe more comfortable with respect to what we're used to seeing, suppose the basis for the codomain is similarly defined to be just the standard basis. Let's say W1 is 1, 0. W sub 2, let's say, is 0, 1. That's now the data that we have to work with. We have our linear map. We have a basis for the domain. We have a basis for the codomain. Let's now see what that might look like in terms of a matrix representation. What is the matrix representation for this linear map T? Well, let's look at what the linear map T applied to the first basis vector looks like. The first basis vector was V1, which was 1, 0, 0, which really says that in our linear map, we simply replace x with 1, y with 0, and z with 0, and so we're going to end up with 2, 7 for the 2 coordinates in our particular R2 or codomain. And now what we want to do is write that in terms of the basis vectors W1 and W2. Well, W1, we just need to scale that with the first coordinate, or W1 is just going to give us information in the first coordinate, and our first coordinate is 2. So that now says 2 times 1, 0 plus 7 times W2, which is only going to give us information in the second coordinate. Or this is now 2W1 plus 7W sub 2. And you could now sort of view that in the following way. You could say, oh, now if I had a basis vector W1 and W sub 2, I can now create 2W1 plus 7W2 by post-multiplying that set of basis vectors by the column vector 2, 7. And that's now equal to TV1, where TV1, written as a column vector, was also 2, 7. So this is now, if you want to look at it that way, this is now the first column of our matrix representation. What's the second column? Well, the second column is going to be produced from TV2, and V2 was simply setting the y-coordinate to 1 and x and z equaling 0. If we go back to our definition, we now have minus 1 and 5 for the resulting two coordinates that map or result when we map the second basis vector through this linear map T, which, if we use the same thinking that we had before with respect to the basis vectors in the codomain, W1 simply was putting information into the first coordinate, and that's now minus 1 times 1, 0, plus 5 times W2, which only allowed information into the second coordinate, so that now this is minus 1 times W1 plus 5 times W2, but we could also write that as W1, W2 being minus 1, 5, and that was now T V sub 2. And this now represents the second column in our matrix. That was now A sub 1, 2 and A sub 2, 2. If we now look at what happens with mapping the third basis vector in through the linear map T, V sub 3 was just 1 in the third coordinate of that basis vector, or in that vector that formed the third basis vector. We now go up and look at our linear map and say, what happens when we set z equal to 1? We get 3 minus 6, so that now T V sub 3 is 3 minus 6, or this is now 3 times 1 comma 0 plus minus 6 times 0 comma 1, or that's now 3W1 plus minus 6W2, or the third column is now 3 minus 6, producing the representation for T V sub 3 in the basis W1, W2. This is now our third column in the matrix. If we put all of those, or concatenate all of those columns together, we end up with 2, 7. That was our first column. Our second column was minus 1, 5. And our third column was 3 minus 6. this is now a matrix representation of the linear map T applied to the standard basis in our domain and the standard basis in our codomain. And this map, 2, 7, minus 1, 5, 3, minus 6, is what we obtain when we have this particular linear map taking us from R3 to R2. And we'll pick up at that point next time.